to module 5. We are discussing about how to interface memory and parallel I/O devices or peripherals to the programmable DSP device. Okay, so this is coming to the point where we are going to have a discussion of interfacing. So we consider a memory device which may be externally connected to a DSP processor or parallel I/O peripherals to a programmable DSP. So let us see how the peripherals can be connected and whether these signals are compatible with the DSP device so that they can be easily connected without any error. So a typical DSP system has a DSP with external memory. So that is what we are going to look into. So DSP will always have an external memory, input devices and the output devices. So these are the peripherals what we are going to connect to a particular DSP system. And whenever we look into the manufacturer of the memory units and the IO devices are not the same if it is compared with the manufacturer of DSP, because the DSP has already studied about the manufacturers. We have three different manufacturers. One is from analog devices, the DSP is manufactured. The other is the Texas Instruments and Motorola. So these three are the manufacturers of DSP. But whereas the manufacturers of the memory peripherals or memory units and IO devices or peripherals are different or maybe same, but most of the times they are different. And we can see that there are a variety of memory and IO devices which are available in the market. Now the signals are generated by the DSP which may not suit these peripherals. Maybe a memory or IO devices may not be easily connected to a DSP. So what we do is there is a requirement of a DSP signal which can be appropriate for setting up a communication with this memory. So whatever we consider in terms of peripherals, those peripherals has to be connected with the DSP device. But whenever we go with the DSP signals, it may not be an appropriate signal which can be used for interfacing. So what we do, we go with an appropriate signal which has to be generated by the DSP processor in setting up a communication with the memory unit. So that is about a memory, how we are going to connect to a DSP. Then if I look into the interfacing process, we can see that there is a peripherals which can be connected in the form of IO device to a particular DSP processor through some interface or through some interfacing unit. And also the program memory or a data memory can be used which can be interfaced to a DSP device. So if I look into this particular process, so peripherals can be interfaced to a processor in two different modes. One is a serial, the other is a parallel mode. So we can have serial communication between a DSP processor and the IO device or IO peripherals. Similarly, we can have a parallel mode of communication done between a DSP processor and the IO devices. And even if I consider a memory is divided into a program memory part and a data memory part. So either it can be connected in a serial mode or a parallel mode. And whenever we consider a serial mode, the data transfer takes place bit by bit. So that is in a serial transmission. In the parallel mode, we consider the word by word data transfer. So whenever I consider this DSP with interface, it can be as this particular interfacing diagram. So we can see that the DSP system is interfaced with the memory as well as the IO device. And then coming to the next, what we have is a memory space organization. Whenever we go with the interfacing process using a memory and IO device, we look into the memory space or what we are going to connect externally to a DSP processor through a peripheral. So through an interface which is a peripheral. Now we are going to use a memory space in TMS320C54 processor. So this TMS320C54 processor is a processor which is manufactured using Texas Instruments, and the memory space availability in this processor is 192 kilovolts. and the size is 16 bits each. So 192 kilowords of information can be stored in this memory space of TMS320 processor, and it is of 16 bit each. So this is the memory space organization of a particular memory unit in a TMS320 processor. And the memory is divided into three different parts. One is a program memory. As earlier I told you regarding the memory classification, it is classified into program memory and data memory. Along with that, we also have a space which is input output space or IO space, and each will have a memory space requirement of 64 kilowords. So that is 192K will be divided into three different memory spaces of 64 kilowords each. So program memory will have 64 kilowords, data memory will also have 64 kilowords, and IO space will also have 64 kilowords. So that making a total of 64K into 3, which is 192 kilowords of 16 bit each. So the actual memory and the type of memory what we consider, it depends on a particular DSP family. So whatever DSP we are going to consider, so that also depends on the family. So whatever we are going to consider in terms of a memory which can be interfaced to a DSP device, it mainly depends on the DSP device of a particular family. So here it is TMS320, so that is a family of Texas Instrument. And if the memory, for example, if it is not suitable or available on a DSP for sufficient for any application, it can be interfaced to any external memory which can be seen further. So whenever we go with interfacing a DSP and it is not sufficient for any application, most of the times it is sufficient, but some of the cases we find that the DSP is not sufficient, or the memory in a DSP is not sufficient for any application. So it can be interfaced to an external memory which can be seen further. The on-chip memory are faster than the external memory. So the on-chip memory is also available and they are very fast compared to the external memory what we interface to a DSP processor. Then there are no interfacing requirements. So whenever we consider any requirements of interfacing, so there is no such requirements for interfacing. So this is about the memory space organization which is required for the TMS320 processor, which can support 192 kilobytes of memory space in it. So considering these three parameters, one is program memory, data memory, and IO space, which is of 64 kilobytes of size each. So they can be used for interfacing with the DSP. And in some cases, the memory may not be sufficient for DSP for some application, so it can be interfaced to an external memory. But also whenever we consider the speed of this external memory, it may not be faster compared to the on-chip memory. So that we have to look into, and there are no interfacing requirements. And because they are on chip, power consumption is less and size is very small. So this is what we consider when we go with the on chip memory. Whenever we consider on chip memory, power consumption is very less. Then the size of that on chip memory what we are going to consider is also very small, and it exhibits better performance by DSP because of better data flow within the pipeline. So earlier we have discussed about pipelining and parallelism concept which was used in the DSP processor. So here also we are considering the same. It exhibits better performance by the DSP because of better data flow within the pipeline. So this is what we consider in terms of performance of DSP. So the purpose of such memory is to hold the program or a code or a set of instructions, and also to hold the constant data such as filter coefficients or a filter order, where we can use it for trigonometric tables or kernels of transformation which is employed in any algorithm. So whenever I consider a memory, it should hold some program, it should hold some program, it should hold a code or a set of instructions, and also to hold a constant data. So these are the major requirements of a memory unit which is used in a DSP processor. It should hold a program, it should hold a code, it should hold a set of instructions, it should hold a constant data, and this data may include a filter coefficients or a filter order. So based on that, we also perform trigonometric functions or tables, that is the kernels of transformation. Whenever we want to apply some transformation process, or we want to have some transformation used in this DSP system, like some transformation like discrete Fourier transform has to be done, or cosine transform has to be done, or any other kind of transformation has to be done. If I consider any application such as image processing, we will go with the DCT, discrete cosine transform. So that is one of the example which can also be used in the form of a transformation here. Now in trigonometric tables, we use a trigonometric function like sine and cosine function. Normally when we go with a DFT process, which is e power j theta, which results in cos j theta and sin j theta terms. So we are going to use it in an algorithm. And not only the constants are stored in such a memory, they are also used to hold a variable data and intermediate results, so that the processor need not refer to the external memory for the purpose. So here whatever we consider, constants are not only the data which is stored in such memory, they should also hold a variable data. It should not hold any data which is a constant, but whenever we perform any operation, the data is going to be changed. So data is a variable. So whenever I consider a variable data, even that data has to be stored in such memory units, and data and intermediate results, so that the processor need not refer to any external memory for this use. So it means that it has to store a constant data, it has to store a variable data, and also it has to store the intermediate result. So the processor need not refer to any external memory for this requirement. For this application, there is no requirement of using a memory. Then this is how the internal memory and interfacing of external memory is done in a DSP. So we can see that there is internal memory which includes memory which is for a program and a data, and also this program memory and data memory, we can see that they are separate and they constitute the internal memory of a system. Along with it has got ALU, arithmetic and logic unit, MAC, that is multiply and accumulate unit, and barrel shifter, and so on. So we can have several computing blocks which can be used along with the internal memory. So together it constitutes a DSP system, and this DSP system has to be connected to the external memory. So external memory interface which can be done for a DSP is as this particular with this example. So internal memory and interfacing of external memory. So we can see that the internal memory is used by the processor, which is faster, which is the on-chip memory, whereas the external memory is not so fast compared to this. So that is how we consider the internal and external memory units. Then external memory is off-chip and are slower memory. So as I told you already, internal memory is on-chip memory and they are very fast compared to the external memory. The same thing is highlighted here, saying that or stating that external memory is off-chip and they are very slow. Then external interfacing is required to establish the communication between the memory and the DSP. So whenever I consider the external interfacing, it is required to establish a connection between the memory and the DSP. So we can see that external interfacing is required in the block diagram to establish a communication, and the communication can be serial or parallel. We have already discussed about that in the previous slide. So external interfacing is required to establish the connection between the memory and the DSP device, and they can have a large memory space. We have already discussed a memory space has got 192 kilovolts of memory allocation, which is divided separately for program data and IO device or IO space. So it is very large. So that is what we understood from this particular concept of interfacing. Then the purpose of this is to store a variable data and a scratch pad memory. So earlier I told you regarding the constant data. So similarly, along with the constant data, we are supposed to store a variable data and as scratch pad memory. So which can store the intermediate results. So after each computing task which is done either addition or multiplication or any other operation which is supported by the ALU of the DSP, then it is used to store the data as well as it is used to store the intermediate result, which is also a data. Then program memory can be a ROM and it can be also a RAM, and this RAM can be divided into two. One is dual access RAM, which is termed as DA RAM. The other one is single access RAM, which is SA RAM. So, or a combination of all this. So program memory can be a ROM, so read-only memory. So we have a program memory which is a read-only memory, then dual access RAM which is separately used along with the ROM. Along with that we are going to use a single access RAM, or it may be a combination of all this. So the program memory can be extended externally. So whenever I consider a program memory, it can be extended externally to 8192 kilohertz, that is 128 pages of 64 kilohertz each. So this is a memory space requirement of a program memory which can be extended externally, and it can be extended externally to 8192 kilohertz. So earlier it was something very less compared to this figure of 8192 kilohertz. So based on that we are going to extend it externally. So whatever interface we are going to consider, so that interface has to be externally done in order to improve the program memory to 8192 kilohertz. So that is 128 pages of 64 kilohertz each. So the arrangement of memory and the DSP in the case of single access RAM and dual access RAM. So we look into the arrangement of a memory and DSP, how the memory and the DSP are interconnected or interfaced, which uses a single access RAM, that is SA RAM, and dual access RAM, which is a DA RAM. So one set of address bus and the data bus is available in the case of SA RAM. So we can see that there is a single set of address bus and a data bus which is for a SA RAM. But whenever I go with the dual access RAM, which is a DA RAM, there is availability of two sets of address bus and data bus. Hence the name single access RAM and dual access RAM. So that is depending on the set of address and data buses which are available. So if it is a single set or one set of address bus and data bus, it is SA RAM. If it is two sets of data bus and address bus, it is a DA RAM. So the DSP can access two memory locations simultaneously. So due to which I can say that the DSP can access two different memory locations simultaneously. So we can see that how they are interfaced. So one is a DSP device. We can see that the address and the data connected to a or interface to a memory, which is constituting SA RAM. Similarly, for a DA RAM, DSP is connected to a memory with address and data, which is with two different configurations, two sets of data and address. So here we can see that in SA RAM it is single set or one set of data and address. So there are 3 bits available in memory mapped register. So we can see that there are 3 bits available, and PMST for the purpose of on-chip memory mapping. So we have already discussed about this PMST process earlier, and they are working in a microprocessor or microcomputer mode depending on a signal activated or deactivated. That is, it might be set or it might be reset. So either the microprocessor has to set or the microcomputer mode has to be set, or the microprocessor has to reset, making the microcomputer mode to be in a set state. So if this bit is 0, the on-chip ROM is enabled. So if I consider this as MP/MC bar, So that is the signal what we are going to use in this TMS T20 processor. Either this bit should be active low or this bit should be active high. So let us see what happens if this bit is active low. So if this bit is active low, that is 0, the on-chip ROM is enabled. So the on-chip ROM is enabled and addressable. So that is what we consider. If this is 0, on-chip ROM is enabled and they are addressable. Similarly, if this bit is 1, then the on-chip ROM is not available. So it cannot be used, it cannot be addressed. So that is, if it is reset, it can be enabled, on-chip ROM can be enabled. If not, it is disabled. And the bit can be manipulated. So there is a possibility of manipulating this bit by a software or a set to the value on this pin at a system reset. So it means that either you can manipulate this by using a software, either you can set this or reset this so that it can enable on-chip RAM or ROM, or it can disable the on-chip ROM, and setting the values on this pin to a system reset. And that is the first bit what we are going to consider. And the second bit is overflow. So that is what we are consider OVL5. So this is the second bit what we consider. It implies it is a RAM overlay. So that is the overflow condition what we have already come across when we discussed it in module 2. So second bit is OVL5. It is implicating that it's a RAM overlay. It enables the on-chip dual access RAM data memory blocks to be mapped into a program space. So it will enable the RAM to map to a program space. So that is what we can understand from this particular on-chip DRAM data memory block, which can be mapped easily. If this bit is 0, so if I consider that this bit is 0, then on-chip RAM is addressable in a data space but not in a program space. So if I consider that this bit is reset, then on-chip RAM is addressable. So earlier we have discussed that if the bit is 0, then on-chip ROM is addressable. Whereas here in this case, if the bit is 0, on-chip RAM is addressable in the data space and but not in the program space. So data space availability is depending on the bit, whether it is 0 or 1. If it is 0, data space is addressable but program space is not. And if it is 1, on-chip RAM is mapped into a program and a data space. So if I consider this, like if the bit is set, if the bit is 1, then on-chip RAM is mapped into a program and a data space. The third bit is DROM. So that is the third bit. So first bit is depending is used for ROM. ROM depends on the first bit. The RAM depends on the second bit, and DROM, that is dual or dynamic ROM. Here we consider it as DROM. So it depends on the third bit. So what it does, it enables the on-chip DRAM to be mapped into the data space. So DRAM bit what we consider here is from 4 to 7. So that is the pin what we are using, that is signal on pin number 4, pin number 5, pin number 6 and pin number 7. So the third bit is for a on-chip DRAM. So that can be mapped into a data space. Now if I consider that if it is reset or set, if this bit is 0, on-chip DRAM is not mapped into a data space. So that is what we consider if the bit is 0. On-chip DRAM is not mapped into the data space. Whereas if I consider the bit is 1, then on-chip DRAM is mapped into the data space. So that is what we consider in the DRAM process if the bit is 0 and 1. If it is 0, it is not mapped to a data space. If it is 1, then only it is mapped to a data space. Then on-chip data memory is partitioned into several regions. So we can see that in the next table. On-chip data memory is partitioned into various regions. So we will just look into the So data memory can be on chip and on off chip. So data memory of 64K, and these are the locations starting from 0000 to 005F, which is 96 locations. They are memory mapped registers. So these locations are assigned to memory mapped registers. Then the next location, which is pointed from 0060 to 007F, a total of 32 locations, which is for a scratch pad RAM. So this is of 32 locations. Then 0080 to 7FFF. So these many locations are used for on-chip RAM. Similarly, for the LSBs 0 to 3, and 32 kilowords of 16-bit each. Similarly, if I go with the next, that is 8002 FF, which is having 32 kilo, the 32K locations, which is on chip DRAM from 4 to 7 for a data. So this is the data memory, which is separated for the memory map registers and scratch pad RAM, then on chip RAM for data. The on chip memory of this processor can have both program and data memory. So we have already considered that earlier. The on chip memory of TMS320 can be for both the program and the data, and it will increase or it enhances the speed of the program execution. So the main idea of this usage of program and data memory as considered as the on-chip memory is that it can enhance the speed of program execution by using a parallelism. That is, multiple data access capability is provided for concurrent memory operations. So it is nothing but parallelism process, what we have already discussed, like accessing multiple data. So that is what here it is done. So it is easy to access a multiple data if I go with the process of parallelism, and it can fetch the data from a concurrent memory operations, that is consecutive memory locations, what we use in the process. Then the number of operations in a single memory access is 3 reads and 1 write. So that is what we are supposed to notice, the number of operations in a single memory access. So we have single memory access and dual memory access, and this single memory access will have one set of address specified earlier. So here, based on that, we see that the number of operations in a single memory access is 3 reads and 1 write. So it can have 4 operations together, 2 operations together. So one is read, one is write. But how many reads? It is 3 reads and 1 write. Then the external memory to DSP can be interfaced with the 16 23-bit address bus and 16-bit data bus. So it can be interfaced with 16, that is a number. Okay, so it is a number, 23-bit the size, 23-bit address bus and a 16-bit data bus. So that is how the external memory to DSP can be interfaced. So but it is compared to on-chip memory, it is slower, but it is required for during the process of interfacing. Interfacing signals are generated by the DSP to refer to external memory. So already we have discussed about the compatibility. So whatever interfacing device or whatever peripherals we are going to use for connecting it or interfacing it with the DSP may not be from the same manufacturer. So there might be an issue or there might be a problem with the signals which are generated by the DSP for interfacing it with the IO device. So it is going to generate an interfacing signal. So the DSP is going to generate the interfacing signal which can refer to the external memory. So what are the signals which can be used? So the signals required by the memory are typically chip select. So we refer it as CS, chip select, and output enable and write enable. So we are supposed to have three different sets of signals by the memory. They are typically chip select, CS, and normally it is CS bar, and output enable and write enable. So one is for actually read, one is for a write operation to be done. For example, TMS 320C5416, so that is C5416 is a processor what we are going to consider here as an example. So which has got 16K ROM, 64K RAMs, okay, each. So it is 128 RAM, which is separated as dual access 64K RAM, and single access 64K RAM. So extended program or extended external program memory is interfaced with 23 address lines. So that is what we are supposed to have. So extended external program memory is interfaced with 23 address lines, making it to 8192 kilo location. So that is the total number of locations after the usage of the memory, which is extended and interfaced with the 23-bit address lines. Then the external memory thus interfaced is divided into 128 pages with 64 kilowords per page. So that is how the external memory interfaced is divided into 128 pages with 64 kilowords per page. Then external bus interfacing signals. In DSP there are 16 external bus interfacing signals. So here we come across the interfacing signals which are generated by the DSP. So here we look into the external bus interfacing signals, because here we are going to use a DSP which can be connected to the external memory. So in DSP there are 16 external bus interfacing signals, and the signal is characterized as single bit, that is a single line, or multiple bits, that is multiple lines or buses. So these signals which are generated can be characterized as single bit or a single line, or multiple line or multiple bits. So it also referred to as a bus, so multiple lines or buses. And it can be synchronous or asynchronous with the clock. So it can be synchronous or asynchronous with the clock. And the signal can be active high or signal can be active low. So there is a possibility of a signal which can be active low or it can be active high. Then it can be an output or an input signal. So it can be output or an input signal. And the signal carrying this line or lines can be unidirectional or bidirectional signal. So either they can only transfer the signal from one point to the other, or it can retransmit using the concept of bidirectional. So it can act as unidirectional or it can act as bidirectional. Then the characteristics of this signal depends on the purpose. So what are those purpose? So we can see the list of signals which are given for TMS T20C54 as in the form of external bus interfacing signals. So A0 to A19, so which is 20-bit address bus. So A0 to A19 will be considered as the address buses, which is of 20-bit. Then D0 to D15, which is 16-bit data bus. So we can see that one is 20-bit address bus, one is 16-bit data bus. Then DS bar, that is data space select. So either we can see that the signal is active low or it is active high. Here we can see that the signal is active low. If I disable this, so that if DS bar is 0, which indicates that data space is selected. Next is PS bar, which is for selecting a program space. So in this case, if I consider PS bar is 0, it means that it is active low, selecting the program space instead of a data space. Then IS bar, that is IO space select, so it is selecting the input output space. R/W bar, which is indicated for a read or write signal. So either we can read a data from the memory or we can write a data into the memory. Then memory strobe and IO strobe. So these are the other two signals which are the external bus interfacing signals which are generated by the device. So in external bus interfacing signals, address bus and the data bus are multi-lines buses. So that we have to look into, if I consider the interfacing of signals, address bus and data bus are multi-line buses. Then Address bus is unidirectional. So that is what we have to consider. Address bus is unidirectional and carries the address of the location which is required. So that is the purpose of using an address bus. Whereas the data bus is bidirectional. So we can just retrieve a data as well as we can just write a data into the memory. So it is bidirectional and it carries a data to or from a DSP. So that is what I mean to say. It is bidirectional. So when data lines are not in use, they are tri-stated. So that depends on the active state of a signal, low or high. If it is active or if it is set or if it is reset, then its operation is considered to be um, active or not. So they are, if it is not in use, they are tri-stated. Then we can see that we have data space select, program space select, IO space select, and they are meant for data space, program space, or IO space selection. So I already mentioned in the external interfacing signals where we come across the data space select signal, program space select signal, or IO space select signal, which is meant for the data space, program space, or IO space location. These interfacing signals are all active low. Then they are active during the entire operation of a data or memory, data memory or a program memory or IO space reference. So it is dependent on the requirement of a memory, which memory is in use, either data memory or a program memory or IO. Read or write signal determines if the DSP is reading the external device or writing. So we can see that read or write signal determines that the DSP is either reading the external device or writing into the external device. So that is what it means. So if this read or write signal is low, then DSP is writing, and if high, DSP is reading. So that is what we have to consider. If this is low, the read write signal is low, it means that a DSP is writing, and if it is high, then the DSP is reading. So that is what we have to analyze based on the status of this particular read write signal. Then strobe interfacing signals. So last at the end we have seen that strobe interfacing signals are available, which is memory strobe and IO strobe interface or IO signal. So both are active low. They remain low during the entire read and write operations of the memory and IO operations respectively. So they remain low during the entire read and write operations of the memory and IO operations respectively. So whenever we consider the strobe interfacing signals, either it is memory or IO strobe signal, they are always left low or kept low during the entire read and write operations of the memory and also during the IO operations. Then external bus interfacing signals from 1 to 8 are all unidirectional. So that is what we look into. All the external bus interfacing signals from 1 to 8. So they are all unidirectional except the data bus, which is bidirectional. So we can see that whatever program memory we are going to use, they are unidirectional, whereas the data bus is bidirectional. So we have already dealt with that concept earlier. Then address lines are the outgoing lines or outgoing signals, and all the other control signals are also outgoing signals. So if I consider this external bus interfacing signals, you can see that data ready signal and hold request, hold acknowledge, micro state complete, interrupt request and interrupt acknowledge, and external flag output, branch control output or input. So here we see that ready signal. So if this ready signal is high, then we can say that the data signal is the signal is ready. The data is signal is ready. If I consider hold bar, it is hold request. Then HLDA hold acknowledge. So it is acknowledgement signal. These two are the active low signals. Microstate complete we are not using. IRQ interrupt request. So whenever there is a request for the interrupt during any operations, whenever any peripherals connected to the DSP device are to be serviced, there is a request in the form of an interrupt. So that is through IRQ signal. So interrupt request. Then interrupt acknowledged. So whatever interrupt is given and the task is completed, it is acknowledged. So data ready signal is used when the slow device is to be interfaced. So that is what we consider data ready signal is used when the slow device is to be interfaced. Then hold request and hold acknowledge are used in conjunction with the DMA controller. So look into this hold request and hold acknowledge signal. Then there are two interrupt signals. One is interrupt request and interrupt acknowledge. Both are active low. Just now I told you about this. Interrupt request typically for a data exchange and for example between ADC and another processor. So TMS 320 processor has 14 hardware interrupts for the purpose of user interrupt. The external flag is active high, synchronous and outgoing control signal. It initiates an action or informs about the completion of a transaction to the peripheral device. So it is normally used to initiate any task or an action, or it can inform about completing any particular task to the peripheral device. So that is the signal what it is meant to send as on when the completion of a task is done. So branch control input is an active low asynchronous incoming control signal. So that is what we consider in the form of branch control input. Then the low on this signal makes the DSP to respond or attend to the peripheral device. So that is what we consider. Then it informs about the completion of a transaction of the DSP. So normally the signal is low, which makes the DSP to respond or to attend any peripheral device. So that is what the low on this particular signal means, and it also informs about the completion of a particular transaction to the DSP. So whenever any task is given and the DSP completes that particular task, then it is going to perform, it is going to inform about the completion of this particular transaction.